Okay, welcome friends. We are discussing about the infinite horizon regulator problem. So, we have discussed the two cases, one the time varying case and the other was the time invariant case. In time invariant case, our problem was for a given system AXT plus BUT and y equal to CXT. We have to find the U, find control law, U equal to minus KXT, where K equal to R inverse B prime P XT. So, objective is to find the UT equal to minus KXT, which will minimize the performance index, minimize the PI, and PI is my J 1 by 2 T0 to infinity x prime Qx plus U prime RU dt. So, in LTI system, linear time invariant system, A, B, C, Q, R are the constant matrix. We have to find out the control law U equal to minus Kx, where K is R inverse B prime P x t and P is the solution of algebraic Riccati equation, which is P A plus A prime P minus P B R inverse B prime P plus Q equal to a null matrix depending upon the size of the P null matrix we can select. So, this is my algebraic Riccati equation which we have to solve. If we can find out the P, we can find out the control law which give me the closed loop system will be now x dot t equal to A minus bk xt. So, whatever be the original system A, if my system is completely controllable, I can control using the K all the state and my matrix A minus bk is a stable matrix. So, A minus bk is stable means all eigenvalues of A minus bk lie into the left half of the S plane, or all eigenvalues will have a negative real part. So, now today we will prove using the Lyapunov theorem that A minus bk is a constant matrix. So, my closed loop system is x dot equal to A minus bk xt. And we have to prove that A minus bk is stable. So, using Lyapunov stability criteria. So, this we will prove using the Lyapunov stability. Let us consider the Lyapunov function as, consider a Lyapunov function so my Lyapunov function, by the definition of the Lyapunov function, let us say V is x transpose P x, as we have done in the time varying case. Similarly, we are selecting a Lyapunov function. P is a symmetric positive definite matrix, x prime x give me the squares. So, this satisfies the definition of the Lyapunov function. So, Lyapunov function should be a positive definite function. So, it is positive definite and it approaches to 0 as x approaches to 0. At x equal to 0, V will be 0, otherwise my V is a positive definite function. So, if V is my Lyapunov function, by the Lyapunov stability criteria, we know if V dot is negative definite, then we said that my system is stable. So, closed loop system we have x dot equal to a minus b k x t. So, next we will try to find out the v dot, this is x dot prime t p x t. If we will differentiate this considering p now be a constant matrix. So, there is no derivative for the p, that will be 0 plus x prime p x dot of t. So, x dot of t and x dot for a closed loop system is a minus b k. We take this x dot as a minus b k transpose p x t plus x transpose p a minus b k. Sorry, this is a minus b k x t. So, I will basically will have x transpose of t, because once I will take the transpose of the x prime, this means I am taking the transpose of a minus b k x t. X t will come here, then a minus b k transpose that will appear in this. So, my expression will be, and also my x t is here. So, the overall expression I can write as x transpose of t a minus b k transpose p plus p a minus b k x t. So, if a minus b k is to be a stable matrix, then a minus b k p plus p a minus b k must be negative definite. So, now we have to show that A minus B k prime P plus P A minus B k is negative definite, and this we can show to show this. We consider ARE to show that V dot to be negative definite. This means A minus B k prime P plus P A minus B k must be negative definite. To prove this, let us consider the algebraic Riccati equation as A transpose P plus P A minus P B R inverse B prime P plus Q equal to 0. So, what we are doing? We are A prime P minus P B R inverse B prime P. This I take at one side plus P A minus P B R inverse B prime P. This I will also take it here. Now, what I have to do? I have subtracted one P B R inverse B prime P. So, I will add 1 P B R inverse B prime P plus Q equal to 0. So, I did nothing, I have added and subtracted this term, rest we kept same. So, this is not going to change, and what we are writing? We are writing A prime P we are taking from out minus P B R inverse B prime P from these first two term. Next term P I am taking here P A minus B R inverse B prime P equal to minus Q plus P B R inverse B prime P. So, let us see what we are doing. We are writing this term, the first term, this term, we are writing A minus taking the transpose of this B R inverse B prime P and whole transpose. So, if I will take the transpose of this, I will get A transpose, then P B R inverse B prime and P here plus this I kept the same P A minus B R inverse B prime P equal to minus Q plus P B R inverse B prime P. So, now in this you will see B R inverse B prime P R inverse B prime P, this is nothing but my K. R inverse B prime P, this is nothing but my K. So, the whole equation I can write as, from this I am writing as A minus Bk transpose P plus P A minus Bk, which is coming here, this equal to minus Q plus Pb R inverse B prime P. So, what was my matrix? A minus Bk prime P plus P A minus Bk. This I have to prove as to be negative definite. So, my this matrix is A minus Bk prime P plus P A minus Bk. So, left hand side Q positive semi definite, positive semi definite, my this whole term P is, send this, my P is positive definite, B prime will give me the square term, R is positive definite. So, my this second term always will be positive definite matrix, positive definite, this means, and this positive definite is with negative sign. So, this shows so this gives me A minus Bk plus A minus Bk prime P plus P A minus Bk is less than 0, means A minus Bk is negative definite matrix. So, therefore, I can say, because my V dot is negative definite, so now V dot is negative definite. So, my A minus Bk is stable. So, by this we can prove that the closed loop system x dot equal to A minus Bk xt, my system matrix is A minus Bk, will always be a stable matrix, whatever be the condition of A, subjected to my system is controllable. If my system is controllable, this means I can shift my state from xt0 to 0. So, what we are doing? We are shifting our state xt0 to xtf, which in this case is 0, because my A minus Bk always is a stable matrix, have all eigenvalues with negative real part. So, in the next, let us take an example to show what we have studied about the linear quadratic regulator system for linear time invariant case. So, in our example we consider a LTI system, second order, x1 dot, x2 dot, t equal to 0 1 So, this is my system, this is my matrix A, this is my matrix B. Objective is to find UT which is equal to minus kxt, which will minimize j equal to that we are taking 0 to infinity 1 by 2 x1 square plus 2 x2 square t plus 4 u square t dt. So, we have to find the ut which will minimize this. So, u equal to minus kx, as we know k is nothing but r inverse b prime p. So, we have to find out the p. Now, in this case, if we will see, eigenvalues of A are 1 plus minus j1. So, this means my original system is a unstable system. So, my first step is to design a control law u equal to minus kx. My system should be a completely controllable system. So, we check the controllability by matrix QC, which is nothing but B AB, and this is equal to 0 1 1 2, and the rank of QC is 2. So, my order of the system is 2, the controllability matrix Q BAB must have the rank equal to the order of the system. Then I said my system is completely controllable. So, it is a controllable system. So, next we will see if we will design a K such that my system is optimally controlled, means my closed loop matrix A minus Bk will be a stable matrix. So, for that we have to find out the P. So, to find the P, solve ARE, which is A transpose P plus PA minus PB R inverse P prime P plus Q equal to a null matrix. So, what is my A prime? A is, so I am writing this 0, -2, 1. So, this is my A prime. P is a symmetric positive definite matrix. So, I will select the symmetric matrix as P11, P12, P12, P22. So, this is my first A transpose P plus PA, P11, P12, P12, P22. A is 0, 1, -2, 2, minus P B, B is 0, 1, PB, R inverse. What is my R? My, this 4 is my R, and from here I can find out my Q as 2, 0, 0, 2. So, P, B, R inverse is 1 by 4, B prime 0, 1. So, P, B, R inverse, B prime, P, P11, P12, P12, P22 plus Q, and this must be equal to your 0, 0, 0, 0 a null matrix. So, now what we know, if we will solve this taking P as a symmetric matrix, total number of equation is n into n plus 1 by 2. So, total equations will be n into n plus 1 by 2, here n is 2. So, we have 3 equations. So, if we will solve this, so we get the 3 equations as so, I will get the first equation by this, second is this is 4p 22 plus 2 equal to 0, and the third equation is minus 0.25 p11 p22 minus 2p 22 plus p11 plus 2p 12 equal to 0. So, if I will solve this equation, I will get these 3 equations. So, these are the non-linear algebraic equation which has to be solved. Sometimes we have to use the iterative methods, sometimes direct solution is available. Like in this case, we can solve the first equation, it is a quadratic equation. So, we get the two values of the P12, out of which we have to select that value which will give P to be a positive definite. So, if I will say equation 1, 2, 3. So, from 1 we get the two values for the P12 is 0.485 and the another value is minus 16.485. Because P12 we retain this value because this give me the P to be positive definite and this value we discard. So, this we will not take. With P12 to be the 4.85, we got P22 as 16.71 and P11 as 34.48. So, you can solve these equations. So, my first step will be to solve the from equation 1, I will find the value of P12 for each value. Basically, I will have the value of the P22 and P11. We have to select those values which is giving me P to be a positive definite. So, by this I can select my P to be 34.48, this is 0.485, 0.485 and 16.71. So, once the P is known, I can find out what actually will be my U. So, to find the U, we can write down the K as R inverse B prime P. So, if I will take this value, R inverse is basically my 1 by 4, B prime is 0, 1 and P, we already find this P, and if we will solve this, we will get K to be 0.121, 4.178. So, this is the value of K. Now, what will be my closed loop matrix? My closed loop system matrix will be A minus Bk and this is, I can write as A is my 0 1 minus 2 2 minus B 0 1 and K I will take 0.121, 4.178. So, this matrix can be solved, and if I will find out and then find the eigenvalues of A minus Bk, which will be nothing but lambda I minus A minus. So, determinant of lambda I minus A minus Bk, that must be equal to 0. This is my characteristic equation, and the roots of my characteristic equation will give me the value of lambda. For this case, this is minus 1.09 plus minus 967 I, and we can see my eigenvalue will have the negative real part. So, my closed loop system is stable, while my original system was unstable, but by implementing the optimal control law we find that my closed loop system will be a stable system. So, I stop here for this class. In the next class we will discuss about how to find out the, or say how to solve the ARE and matrix differential Riccati equation using some analytical approach. Thank you very much.